Back for another episode of AI and Robotics series. And we are very welcome and very glad to have Maria Bauza from MIT here. Maria is a PhD student with Alberto Rodriguez at MIT in mechanical engineering. She got her undergrad and master's degree from Polytechnic University of Catalonia, and then she was visiting student at MIT as well. She works on a very exciting area of developing algorithms to make robots more reactive, particularly through feedback, but the feedback is both visual and tactile. Along the course of her work, she has done some exciting work and won awards, including Best Paper Awards at IROS, and she was part of the Amazon Robotics Challenge team that won the Best Systems Paper Award. And she has been rising stars in mechanical engineering. And so broadly, listing the awards aside, one of the things that I'm particularly excited about is the work that she has done on both not only just building realistic systems, but adding the sense of touch in picking, which has enabled a number of interesting directions or skills in robotics. We are very glad to have you here with us, Maria, and love to hear from you. Thank you.
Thank you, Minesh, and thanks a lot for inviting me. So as you have said, I am a PhD at MIT working with Professor Alberto Rodriguez, and my research aims at doing robots be more dexterous through manipulation. And for that, today I will focus more on how we can use tactile to achieve this goal. So let me see if I can go through my next slide. There we go. I think we will all agree that humans are very good dexterous manipulators. We are accurate and fast. And actually, you can see this video how humans can manipulate objects very easily. And they do so not only by using vision, but also by relying heavily on how they make contact and how they use their touch senses. Moreover, I would argue that when they do those actions, they are not just trying to fulfill the next goal, but they take into account also all the limitations and requirements that even their own capabilities and the task itself has. Like for instance, in this video, sometimes the worker does a regrasping hand, or sometimes it even grasps two objects before trying to place them into the board because that becomes more stable to place both objects at the same time. And it just is not only this, sometimes when we do cooking, we also grasp another handle of the pan so that we can make sure that when we are stirring something, things don't fall apart and things remain as we wanted. So again, when we decide what actions to take, there is a lot more involved than just finishing the goal that we have in mind. What about robots? Well, for robots, I think it has gone a bit differently. We are not yet there. But one of the successes that I've seen during my years in research is bean picking. Bean picking to me started to gain a lot of momentum through the Amazon Picking Challenge, which goal was, I'm giving you this bean, can you drop it? Can you make an autonomous system that can empty this bean? And this was our solution from my lab in 2017, where we built this robot that, as you can see, its only task is go into the left bin, try to catch as many objects as possible, and just drop them into another bin. It doesn't need to care about where are the objects, where they are placed, which object is grasping. All it needs to do is empty the bin, doing a stable picking. And we could do that fairly well. We actually can empty this bin with ease. The objects are unknown. And this has worked well. This has gone into companies. We now have startups. We have even more traditional companies like ABB already deploying those things into real industry. But when things go beyond picking and just a stable picking, I think they get much more involved. And I just wanted to show you an example of how this actually gets more involved. And I'm just going to consider a Crayola. And this is going to be my robot. Just for the illustration, a parallel GeoGripper that you can imagine is attached to a robotic arm. So now let's say that we only want to pick the Crayola. Our task is grasp the Crayola. Then there's still going to be some requirements on some ideas on how this task will work. We know that if we grasp at the center, this is likely to work. If we grab at the tip or bottom, this is likely to be less stable, but ideally this should still be fine to some degree. But what if now I ask you, can you grasp and tell me where is the Crayola with respect to the robot? Then you start having perception requirements. you will probably need some sort of perception system. And if you think about tactile, what might happen is that tip and bottom are actually reasonably fine to localize. And this is because what we call these are unique contacts. If you touch the tip, that contact, that observation will only happen at the tip. No other part of the Crayola is going to leave you that impression on the sensor. Instead, if you grasp at the center, this is what we call non-unique, because it's true that you might be able to differentiate this contact from this other one, but probably you won't be able to differentiate these two. And this is what we call non-unique, when two different poses of the sensor with respect to the object lead to the same or very, very similar tactile observations. And this is very important because this is not something that we can get away. This is an intrinsic property of tactile. Tactile is local. It's highly discriminative. When you have something that is unique, it can really tell you what it is. But when there is these non-unique cases, then tactile has this property that there is some uncertainty about where you are making contact, and you have to deal with that. This is a requirement on your perception. But it's not just that. Imagine you have other tasks. Imagine you want to paint or you want to store this Crayola. If you look at it just from the final grasp, those are already different. Painting might ask you to grasp it from the bottom, storing from the tip. And this is already something that you need to take into account, but if you just look at the storing, there is much more. You also need to reason about where you make contact and how you're going to move your robot to achieve the final position. And just like in another example, let's say the Crayola is on the floor and we want to do two grasps. Then one way to do it would be you first grasp it from the bottom, lift it, and then suddenly you have another set of contacts that allow you to just grasp it from the other side, from the tip, and now you can just rotate it and put it back. Okay, that works. But I think you might have realized that you could actually do the same, but just with a single grasp. And in this case, you could do something like this. You just grasp it from the tip, rotate it, and put it back. That's faster. So if I were to ask you, is this the better solution? I think naively we could just say yes. Less contacts, faster, probably better. But actually, I think it depends. And it depends because you need to take into account what is the task and what are your requirements. If you are going to enter into collision by going into a single grasp, then that's not the best answer you can give. If you have that the box is farther from the robot, then that extra contact that you're making might give you more reachability into the box. So again, it's not a straightforward answer. It's going to depend on the task, but we need to take into account again that our actions really depend on the limitations and the requirements of our system. So in this talk, I'm going to talk about mainly two things. The first one is going to be how can we add these requirements into solving our task? And for that, I will center on the idea of kitting. Kitting is going to be precise pick and place. So we want to be able to solve the task of pick and place very accurately. And for that, we are going to use tactile. Tactile is going to be our main source of perception. And that's why in the second part of the talk, I will go more in depth into how we can do tactile localization. How do we go from those tactile observations to describe where we estimate is the pose of an object? So I'm going to go through these two, and I think they are linked together. So hopefully we will see how tactile really can impact how we improve manipulation. So let me go back into the idea of what is kitting. Kitting is going to be composed of a few components. The first one is picking. You're going to have maybe some clutter of objects, and you want to pick one of them. After that, you want to use, in this case, it's going to be tactile to localize what is the object. And once you have done that, ideally, you would just like to go and place it. You can see that there are already some objects placed in data. But what may happen is what I was already arguing before is that sometimes you might need to do some extra actions before reaching into the configuration. Depending on your pick, it might be possible or not to place it directly. And if not, you might need to use something else. Like in this case, it could be a regrasp. So main challenge, kitting is not as straightforward as a stable picking. And what happens, as we all know, is that when the task becomes complex, then data in the real world becomes more expensive. It's harder to get. So how do we go about that? And our decision on how to aim at kitting is to propose to build a digital twin. That's basically reproduce your system, but on simulation. And basically, the main assumption that we are going to take to do that is that we have access to the geometry of the objects. this is an assumption that can be seen strong, and probably to some degree it is, but it really helps us move all the computations into simulation. And it's actually more reasonable than what it might seem. If you go into industry, most of the objects that are being manufactured, you actually have available all the models and all the geometries because you had to manufacture them. So you have those geometries. So once we have that assumption, again, we can move most of the computations, if not everything, into simulation. And now, again, our goal is we are going to simulate everything. We are going to simulate the entire task. That's going to give us access to a lot of more data, taking into account all the requirements of the system. So if Tactile has this property of non-unique and uniqueness, that has to be also in simulation. And finally, our goal is going to be, can we find solutions that we know are very likely to transfer into the real world? Because of course, the goal is never to solve simulation. This goal is to have systems that work as precisely and accurately as possible into the real world. Okay, so this is how our digital twin looks like, and there's going to be some requirements. And among those, one of them is going to be depth information. We are going to use some depth information at the beginning to decide how to establish the grasp. And these are just how the real images look like. This is how simulator look like. And then you can just apply a small transformation to make them match. So that again, the gap when you bring things into real world is smaller. The most important thing now is how do you go about tactile sensing? And for that, what we do is we say we are not going to try to simulate the whole tactile image, the whole observation that comes from a tactile sensor, because that one is very complex. It has a lot of information. Tactile observations can give you even force distributions, sleeping. What if we just go and try to estimate contact? We just try to use contact instead of the full tactile image. Then what happens is that you can simulate this contact. If I give you a pose of the object with respect to the sensor, it's possible for you to tell, oh, these is the places where the object is going to contact the sensor. And these are what we call the simulated contacts. So this is how we go about tactile in simulation. But there's going to be many more. You have to take into account kinematics of the robot, whether there's going to be collision, whether grasps are going to be stable, whether the motions that you're going to do are going to be feasible. And all those things we have to capture into simulation. I just want to make it clear, for this task, we didn't find necessary to use a physics simulator, but this is something that could definitely be involved into this. If we think that physics and dynamics are going to play a big role, then adding physics simulation makes a lot of sense. Just that because most of these actions are relatively low in dynamics, then you can go ahead and just model some of the parts where physics are important, but without having to rely on doing all the pipeline into a physics simulator. Okay, so this is how it looks like. This is kitting. We are grasping this object. Once it's big, we actually do tactile observation. We try to guess and estimate what is the pose of the object. And now, if we cannot yet place it, it has to be placed at the center. What we do is what we call a regrasp. And here you can see the robot just regrasping this object. And now it's at the right configuration so that kinematically you can reach the desired pose, which in this case is just vertically on the center of the object, as you will see now. So this is how it looks in simulation, and this is our goal. We want to find solutions for this that then can transfer into the real world. And now our proposed solution, it's something that is based on something that has been studied for a while, which is DexNet. And I think Aminesh also did great work on this, which is you take a depth image of the situation. In this case, there is a single object, but you can imagine that this could also apply when there is clutter. And you try to sample and score grasp. And the way we are going to score this grasp is taking into account the system requirements, the limitations of perception, the characteristics of our motion planner. All those things are going to be taken into account when we try to say, is this grasp better than this other one? And the main idea of how this goes, because again, I want to spend more time talking about tactile localization, but just to give you a flavor of how we solve this grasp scoring is we see requirements as objectives, as kind of a score that maybe goes between 0 and 1, and you want to maximize it. So then our goal is to learn a neural network that is capable to predict, given a grasp, what is the objectives value. So how good is going to be a grasp, how good is going to be tactile localization. We are trying to capture these ideas through these objectives values that are learned through a neural network. And then all we have to do is sample graphs and try to obtain the one that maximizes our objectives. In this case, we use the product of the objectives, but definitely there could be nicer ways to do it. And I think because we are doing simulation, we can explore which is the best combination. But just for simplicity, let's say that we just multiply the objectives and we're trying to find the graphs that maximize all of them. So now we have this final graph. And I want to show you some qualitative results, because why is it important to take all the requirements into account? Well, for this object that looks kind of a big Crayola, if you only take into account grasping, is the grass going to be stable or not, you get a really nice centered grass, which is likely to be stable, but it's actually not going to be that good for perception. It's going to be likely non-unique. If you now take into account perception, then the edges become much better, but this is probably not such a stable grasp. It's kind of tilted with respect to the object. Similar happens when you think about motion planning and how many regrasps we're going to need. And if you combine them, as you might expect, you get a much nicer grasp that is likely to be stable and is definitely going to give you good perception. So these are the things that we gain just by combining our requirements when we try to decide what actions to take. So now that we have this, we just need to decode the grasp. This is not anything new. We just take those depth images. As you can see, the red flash is kind of the camera taking the depth image, and now we can just go and pick the object. So that transfers well. There is nothing especially new in how we do that. But then once we have done this, and we have already grasped the object, then the next question is, now we need to localize it, because we want to do precise placing. And precise placing requires a good understanding of what is the object. And finally, what we need to compute is, once we have this object posed, how are we going to place it? In the video, what you just saw is that if you can find the best actions, you often can escape doing a regrasp. But in case that is not optional, then you need to be ready to perform a regrasp. And that again requires you to understand what is the pose of the object. And this is just how it looks in the real. Now you have this object in hand. And in this case, I just put a case that is very challenging because the object is not exactly where you would like it to be. So you need to perform a first grasp so that finally it can do a second one. And now the object is where it needs to be so that we can go and place it at the desired position. And again, as you can see, this is accurate placing. The insertion is not trivial. So you need to make sure that your motions and your perception are good, so that you don't go into errors that really make you not success at the goal of placing. And again, all of this is just learning simulation, and then the hope is that it transfers well, as you can see now, into the real world. So I have not talked yet about tactile localization, but as you can imagine, this is the most important thing that we need to when we want to have high accuracy. So let me now just spend some time on tactile localization. And the main idea is this one. You are given a tactile reading, and you want to be able to solve this problem. You are touching the sensor, you're getting these observations from tactile. How do you identify the pose of the object? And previous work, there is a lot of previous work on tactile localization, but mainly I would say that either they rely mostly on vision and use tactile as a complement, or instead they require to use a lot of real data from the object that you're contacting. And that is a problem, because instead what we would like to do is what we call localization from the first touch. You give me an object. In this case, we're going to require you to give me the geometry of the object, but then the first time that you touch the sensor, you will be able to localize it. And that is much different to previous approaches that you need to first go and explore the object until you're capable to do a prediction of the pose. In this case, the first time that we touch it, we should already have enough tools to say this is the pose. So how we go about that? The idea is that we have the object model, and now we can simulate contact poses. These are poses where the object and the sensor contact. And from those, you can identify in the form of depth images what is going to be the part of the object that makes contact. And this is what we call contact shapes. So now we have these contact shapes that we can just compute in simulation very easily, and we can compute as many as we want. And in practice, we're going to compute a dense set of poses. On the real side, what we do is we get those tactile observations, and then we use a neural net to estimate the contact shape, to identify which parts of the object are making contact with the sensor. How is this neural net trained? Is very easy. We just need to do it once. It's kind of a calibration step. And it works like this. We have this platform that basically moves this board, this red thing that you can see, and just moving it, and while it moves, it collects tactile images from the sensor. But at the same time, because we know the pose of the sensor with respect to the gripper, we can also use this geometric contact rendering to identify the contact shape. So the contact that is supposed to occur because we know the pose of the object with respect to the sensor. So now we have this pair of training data that we can collect for any objects, but then it works well when we provide a new one. Why is that? That is because what contact happens is object independent. It doesn't really matter if you are using a screw or a ball. What it matters is, can you identify if there is contact or not? It's a more binary question to some degree. So with this training data, we can train once this neural network as a calibration step, and then we are good to go. And as I was saying, this is object independent. That's fantastic. We don't need to collect extra data for new objects. And the other part, which is object dependent, is done in simulation. So to some degree, it's free. We don't have to spend time in the lab engineering anything to get all these simulated contact shapes. And now, how do we go from this to tactile localization? Well, the main idea is that you want to do tactile image matching. That means you just want to find which contact shapes that you have simulated are more similar to the one that comes from the real sensor. And for that, we learn a neural network that works as this. The neural network is basically going to do the matching, so it's going to give us probabilities. And at training time, the way it works is we have this dense set of pre-computed contact shapes. These are just many contact poses between object and sensor, and we sample a new one. And we identify which one is the closest in the dense set that we pre-computed. And we assign a label that gives 0 to all the contacts except the one that is closest. Once you have this, you can encode them, and that gives you some embeddings for each of those contact shapes. And now you can just use a softmax and compute predicted likelihood. And basically you get this new set of probabilities that you can compare with your label. And by using cross entropy, you can just propagate the loss back and train your encoder. This is at train time, and you can do this in simulation, and you can train it as much as you want. And then at test time, what happens is that now you get the contact shape that is noisy, it comes from the real sensor, and you already have all the pre-computed encodings. So basically, all the encodings from the dense set you already have computed previously. So at test time, all you do is you pass it the new contact through the encoder. Then you do matrix multiplications to compute the differences, and that gives you the predicted likelihood. So now what you can do is say, oh, actually, if I, for instance, look at the best likelihood, this is actually the closest match. And because each of those contact shapes is linked with a pose, you now have the pose, your estimation of the pose of the object with respect to the sensor. So this is what we are doing here. We're just assessing probabilities of each of those contact shapes to be the most similar to the one that comes from the real sensor. We do an extra step, that is what we call registration, because these contact shapes actually can be seen at depth images, and depth images can be seen at the same time as point clouds. So point cloud registration is useful, and you can use it to just refine a bit more the pose and go beyond this predefined set of contact poses. But finally, what is important is that you get a pose distribution. Basically now you are not just giving me a single estimate, but a set of poses, which is really important, especially when you have non-unique contacts. When one contact can belong to several poses, it is nice then to have a pose distribution, because hopefully all those poses that could result in the same observation are all going to be the most ranked, the higher probability.
I have a question.
Yeah.
So on this setup, when you do nearest neighbor matching in your data set, before the registration step, does the dataset contain all of the potential poses, or in the same object in many poses, or
so
that's question one? Yeah.
So I think the dataset would end up being this dense set of contact shapes. And for that, what we do is we discretize the space in the form of a grid. And we make sure that each pose inside the grid, its closest neighbor is around 1 or 2 millimeters. The more, the bigger, the denser the set, so meaning the closer each element is between each other, or the nearest neighbors, the closer they are, then the higher resolution you can get on your predictions. So this is
Okay.
what.
And then when you do matching in the next slide, so not matching, registration, sorry.
Yes.
So which was a rotation. How much is it constrained rotation? Do you constrain how much sort of, how much can you deviate from prediction? Or so when you're doing registration to what?
So we are registering the one that is coming from the real sensor with respect to the match. And what happens is that if the initialization is good, meaning that this is a good estimate, this registration actually can help you. And you don't need to bound it. If things, if the initialization is not that good, then registration doesn't guarantee you at all that it's going to do any better.
Thank you. Carry on.
Thank you. So now we have this post distribution. And I just wanted to spend some time stressing why it's important to use this embedding to go from just those images, those contact images, into embedding them into some space. And the first one is because it makes things faster. Now you just need to do a pass on the network and then just do some matrix multiplications to compute probabilities on a large dense set of poses. It's also because it allows you to adapt your computations to this kind of weird metric, which is pose distance, because you're comparing two images, not on how pixel similarity, not on how similar they are in terms of pixels, for instance, but in terms of how similar are the poses that generated them. And that is something that using embeddings becomes very natural, but otherwise it would be extremely hard to even formulate. Another reason is because we are using images, and images have the property that we know work really well with learning algorithms. And especially contrastive learning has had a lot of success. And it turns out that by using some of the techniques, we can actually very easily get better results. So in this case, this approach is based on something that comes from the computer vision literature and contrastive learning, which is called MultiContact. And finally, because this gives us an efficient way to get well-posed probabilities. And that means that now our tactile localization can be embedded into much more complex systems like Bayesian frameworks, where you have other set of constraints, other set of distributions, and you want to combine them to provide a single probability of where is the pose of the object. And I just wanted to emphasize this more on how you can add post constraints using our algorithm. And I will show you that in the case of a multi-contact setting, which means now you have the object that is being contacted by more than one sensor. And that means that at each time step, you're going to get more than one contact. You're going to get several
question
contacts.
On the previous slide. When you talk about contrastive models, usually the assumption is that in your initial pose dataset, you do not have poses. You would most likely have a data set of objects in varied poses, but you do not have ground truth. So the embedding that you learn from this can still be used for doing nearest neighbor lookup, but you don't actually have an explicit pose until you have the label for the original data point. But if you have the label for the original data point, why not use it for regression?
Because I think this allows us to better exploit the model. Like one option would be, if I'm understanding you correctly, is just try to predict the poses of the object based on the images. But that actually loses the capability to exploit the object model. In this metric where we are using this comparison between images, we can very easily exploit the object model, which allows us to also better reason about non-uniqueness. If you just wanted to predict a single post, then we have tried that. And it actually, the network becomes much more confused because now you're not using that ideally the object model, which gives you a lot of information. You're just trying to do blind regression, and that doesn't perform.
But you don't use the object model here either, do you?
We do, because each of our embeddings is computed from the contact shapes that come from the model of the object.
Okay, got it. Thank you.
Thanks. So just as I was saying, now we have those distributions and we want to combine them, because now we are going to get several sensors. Each of them is going to be providing us a contact shape. And this is what we want to compute in this case. We want to understand what is the probability of a pose given all the contact shapes that we are getting from each of the sensors. And if you do the math, this basically reduces to this expression, which is a multiplication of terms, where the last one is just any prior, any pose constraints that you know. If you know that one pose is more likely than another one, then this is what you can add into this term. And the other ones can just be computed using the similarity function, just this encoder that we already talked about. So suddenly multi-contact sensing becomes just a straight multiplication of different probabilities that you can compute using this single encoder that you have.
So this is a sequence of contacts or the same object contacted by multiple sensors?
In this case, we consider multiple sensors at the same time. But I would say that probably if you have multiple coming, probably the math is not going to look that different because this is just tracking. So these are some qualitative results. Here you can see how it works. So as you can see, this is the first time that we touch the sensor with this object, but we can still produce good estimates of the pose. And we've done this for several objects. And now I'm just going to show you the qualitative results for all of these objects. And overall results are good, especially when the contact is unique. You can very well identify where it's happening. But then when objects are a bit bigger, usually they tend to have more non-unique contacts, and trying to do pose estimation from just a single contact becomes harder. So then is when it makes sense for you to start reasoning about what are the constraints that I could add to help my perception do better. But usually, again, when contacts are unique, the algorithm can really perform extremely well. And otherwise, we have distributions to just reason maybe over time or over multiple contacts or other systems, what is the best pose estimate.
Do you ever have to reason about which object you are using, or do you always know what object is, but the only confusion is pose?
So for these results I'm showing, we just assume that we know the object identity, but in practice, you could just imagine the most naive approach, which is you could now just have the contact poses that then set that we had for each of the two objects just combined. And now you would need to run things not just for one set of contacts, but for the two that come from the two objects. And in this case, again, I think what will matter the most is, are these contacts that you're making with each of the objects unique or not? And if they are unique, I think object identification is not going to be a big problem. But if you have two objects that are very similar, then that would be probably something to be concerned about.
So just to go back in terms of the model is trained separately for each object, or is it the same model for all objects?
No, we are training it separately because this model is only trained in simulation. So it makes sense to us that we just want to exploit and be as good as possible for just a single object. You could try to train it for several ones. I think as long as I think if you want to train it for 2 or 3 objects at the same time, you're going to be fine. If you want to train this for 100 and thousands, I think that you're going to run into issues because the capacity of the network is finite.
How big is the data set for a single training run, in the sense that for a single object, how big is that data set?
So the training data can be larger, but in terms of how many contact poses we use, so how many poses we are comparing against when we are doing the matching, it depends on the object size. For smaller objects, it's on the order of 7,000, a few thousand. For big objects, it goes around 20,000. So it's big, but it's not extremely big. So you can still do things in real time.
Very good, thank you.
Thanks. So now I'm going to show you quantitative results. And on the left axis, on the y-axis, you will see normalized pose error. That basically is a way for us to take away the size dimensions. And one is basically when you try to just give a random pose of the object. And then red is because we have this dense set of object poses, if you were to just pick the closest one. And now what I'm going to show you is a violin plot of the pose error distribution. And as you can see, most of the errors are small. If you look here in millimeters, they are usually, I think the mean and the median are on the order of a few millimeters, like 4 millimeters, I think in this case. But then there is also the chunk of distribution of errors in here, which basically is due to this non-uniqueness. There are some parts of the object that are actually non-unique. So two poses of this object actually result in the same tactile observation. And what that means is that you sometimes get into the other pose. If there are two poses that give you the same, half of the time you might be able to get it, half the time you might not. And this is something that is a requirement, is a property of tactile. Tactile has its own uniquenesses, and from just a single contact, I would argue that it's impossible for you to really tell in those cases what is the actual pose. And if you do registration again, you can do much better, or you can do better on things that are already close to the true pose. But in this case, there's no way for you to move from one side to the other. But then here I'm showing what happens if instead of reporting just the error of the best match, you take the 10 best and you report the minimum error among those 10. And as you can see, these errors here disappear. And that's because now in a set of 10, it's likely that all the poses that would produce the same tactile imprint are actually contained in this set of the best 10 matches. And that's why now we see that only by considering 10, and again, this is 10 out of maybe 10,000. So there's still a very small set of your possible poses, but you still can get completely very good estimation just by taking the best 10. And we've done this for other objects, and as you can see, the idea is the same, right? Some objects are going to have very clear non-uniqueness, and you have this distribution, but just by considering a few more than just one best estimation, you clearly can see how this non-uniqueness or how this multimodality just disappears, and now you have most of your distribution centered around 0. This object is a bit more complicated. That's why we put it in here. It has plenty of non-uniquenesses, and even if you consider 10 of them, you still will see that there is still some cases where it's hard to identify properly the pose. But what I can say is that we have results that I haven't shown in this presentation, but if you add 1 or 2 more contacts instead of just a single one, you can already identify with high accuracy what is this object. So again, we are doing this from the first touch and just with a single sensor, but at the moment where you add more contacts, then things rapidly can be easily identified, even for objects that are like this one, which can be complicated just from a single estimate and a single contact. Okay, so now I will go back to kitting, just very briefly, just to say that we have been using tactile in kitting for 2 things. The first one is because we require accurate pose estimation, and tactile is a source for us to get these estimates, but also in a different way, which is what we call tactile observability. We have been using tactile to tell us and to guide us towards graphs that are going to lead us into better pose estimations. And that's one of the things that I think we should look more into. We know that tactile has some constraints, has some limitations. If we can take those into account and then exploit actions that give us better observability, we can get in the end better task success performance. And this is something that I'm really interested in. So I'm just going to conclude here. What is next for me? I've been always really interested in perception for manipulation. So I already have some work going on combining tactile and vision. I think the same framework that I explained today will work very nicely with a combination of the two. Tracking again makes a lot of sense, right? We were just doing things for either one contact or multiple contacts at the same time, but we know that if we can combine information over time, that gives us much more. So we are also working on how can we make tracking as fast and reliable as possible. And finally, I'm really excited to look into the direction of what happens when you don't have this assumption of known objects. What happens when the model is unknown? And we have presented some work, we will present some work at ICRA this year on how we can actually recover the pose and the shape of planar objects when we are pushing them. But this is for planar objects. I also think that when we look at 3D objects, there is also hope that you can try to recover the object model and very rapidly start also providing pose estimates. So we also have some work that is trying to reproduce or recover the object models while we at the same time we're trying to use tactile to identify its pose. And more in the long term, I think system level optimization makes a lot of sense. And here I'm just gonna remark 2 things, which is that each task and each system is gonna have different requirements. Like we have seen that tactile has some requirements, collision checking has some requirements, but the hope is that even though those requirements might be different depending on the task and the system, how we combine them and how we exploit them to find better actions that can be task independent. And this is something that I really want to look more into, especially for the case of tactile, where we really understand what are the limitations and the constraints and the good things from tactile. And then second is that if you really understand your system and you really can find the actions that make you get closest to the task, you hopefully can also go back and say, what are the limitations? What are the things that are constraining me from getting high accuracy? And I think there is also hope that in the long term, we try to identify and improve our systems and say, I think this model is failing at this step. Can we just maybe collect some extra data, either in simulation and in real, so that we can just improve the overall performance of the system? So targeting what are the cases where things are failing so that overall you get an improvement. So with this, I'm going to conclude. I'm happy to now go into discussions and take any questions. And thanks a lot for having me.
This was a wonderful talk. I think this was very interesting and engaging to build practical systems. Before I have many questions, but I will give others an opportunity to ask their own. So any questions from the audience first?
I have a question kind of just about, maybe I forgot you mentioned in the beginning, but like the actual sensors themselves, like how does that work?
Yeah, I should have a slide on that. The sensors are extremely simple, which is fantastic, because when they broke, it's very easy to fix them. They don't break almost ever. The idea is that you have a membrane and you have a camera. And now when you touch the membrane, you can see it on the other side, how contact is happening. And then all you are doing is recording that deformation with the camera.
So does that mean that the actual surface that it's contacting, is that like rigid or is it like soft?
Even in between is a bit soft so that it can deform, but it's not super deformable because in the end you want it to go back to the initial pose. You don't want to start this data. So it's deformable, but it's also elastic so that it goes back. It's an elastomer.
So are you building the like sensors yourself or are they like off the shelf?
We are building them. My lab has already done a lot of work in building them. Now we're at the point where manufacturing them is extremely easy and also very cheap. I think we were talking about this the other day, and right now, because not everything is automated, like at the commercial level, it would take $100, which is still super cheap. But I think if you wanted to make them even cheaper, I think $20 would be like a goal that is totally achievable. So we are building them in place, but it just requires you to 3D print the mount. Then you just need to manufacture the membrane, which is an elastomer. So it's a very simple chemical reaction that you can do. I wouldn't say at your house, but almost. And then the cameras you can buy, and they are really cheap. This is one of the nice things about vision. Vision has rapidly improved over the years, and cameras are not an exception. So you can get really good cameras at very low cost. So you need a camera, the mount, some electronics, but that's again super cheap, and then just the membrane. Those are the main components of your sensor.
Thanks. Yeah, that's really interesting. I think Hannah has a question.
Yeah, thank you. No, thanks for the great talk. I wanted to ask about the grasping force. Like, do you have limits as to like for these sensors, if you're grasping like soft deformable objects, like what's the grasping capacity? And then like how hard do you need to grasp objects to be able to identify them through tactile information, I guess? And do you consider forces in your gripping?
That's a fantastic question. The answer is we consider them yes and no. You don't need to apply a lot of force, and actually you can design that membrane of the sensor to be more or less stiff. If you make it really stiff, then you're gonna need more forces. If you make it really soft, then just a small pressure on the sensor is already created deformation. So that's depending on your test and depending on your goals. You can already engineer your membrane so that you don't have to exert that many force when you don't want to. And the way we treat this because in real settings, we won't know exactly, or we don't have to know how many forces being applied on an object, and we still want to be able to do tactile localization. So in these cases, what we did, and I didn't go into that, is that when we do the training of the neural network that does matching, instead of just saying this pose can only produce this contact shape, what we do is, what is the set of contact shapes that could be produced depending on the force that we would exert on the sensor. So for each contact pose, we actually, even though they are all embedded into the same embedding, they are all encoded into the same embedding, we do allow us to consider different forces. And basically, the more force you apply, as you can imagine, the more regions of the object that you can see. So this is how we take into account force.
Great, really cool. Thank you.
Thank you.
I think Chris has a question.
Hey, yeah, thanks for the great talk. I'm curious about the combination of vision and these tactile sensors. I'm wondering if you could just elaborate a little bit more on what the joint system that you mentioned that you've already like kind of started working on would look like, and how you leverage vision to, I guess, improve the precision of your estimates.
Yeah, that's actually an excellent question. I'm really interested into combining tactile and vision. I think a system that only has tactile is good for research, but it's not good in practice. You always want to have vision supporting you. So how we go about adding vision? Vision is actually kind of very different from tactile. If you think about tactile and a distribution that comes from a tactile localization, it's probably kind of peaked. It's very accurate because once you touch a place, you can really say it's here or it's not, but then there could be multiple pauses. So there's no uniqueness that we were saying. Instead, vision is more the other way around, where when you see an object, you might have some uncertainty. So maybe you have a bit more of uncertainty, but it's kind of unimodal. There is like chances to have this. So distributions are very different. But I think as long as you are willing to use distributions, you are good to go. So for vision, the way we are going to do it is we want to have not only for a contact pose, the contact shape, we also want to simulate the depth image. So now this pre-computed set is not only contact shapes, is also depth images. And you can imagine that, I mean, there are two ways to go about this. Let's say that you want to make the easiest one, which is you grab the object and now you always go to the same pose with respect to the camera. Now there is only a unique depth image that could be generated because you know your robot and you know your, and you know the camera. So the object, you can just find what is the point cloud that belongs to the object. And this is the easiest way to go, because now for every contact pose, you have a single depth image and a single contact shape that could occur. And now when you're doing the comparison, it's just all the same because they are all just images. So you just embed them into the same place. If you want to consider cases where actually the orientation can change of the object, then it becomes a bit more involved. But there's actually really nice work on computer vision that have already tackled this problem. And what they do then is they just try to identify what is the orientation of the object. So the pose of the object might change, but you try to still identify what is the orientation. And that is still a kind of narrow and simple problem. And you again do contrastive learning. You just say, okay, this is the orientation that I would expect, and then you compare it with the current point cloud of the object, and then you do matching data.
Okay, thank you. Yeah, yeah, because I was curious about I was thinking about the case where like you have screws of various different sizes, but like the same shape essentially, and like vision without the depth. I think you answered my question because I was considering like the different scale spaces of them, right? You could get confused amongst the different scales.
Yeah, but
so,
yeah, go ahead.
Yeah, so you mentioned that the sensor, the vision sensor that you acquire depth from would have to be in the same position to kind of lock in that scale. What about when you're if you wanted to move that that camera?
I think when you want to move that camera, you're still gonna have something which is, I mean, I'm gonna make an assumption here, which is, let's say that you also have contact, that you also have tactile information. That also means that you're in contact with the object. And because you're in contact with the object, you know much more. You know where the object is gonna be, you know what are the dimensions of the sensor. So you can get much more information about what is the sensor, because you have an extra constraint on tactile that really, I think would collapse what are the possible sizes of your object. So even if the robot is moving around, because you know that you're making contact and you know where is the robot and its dimensions, I think you're already gaining a lot just from there.
Okay, cool. That makes sense. Thank you.
I have a question. I'm a bit confused about what the benefit is of the neural network. You said it's to improve the speed. So I think one neural network is to process the image from the sensor. And do you think that could be replaced with the standard computer vision like filter? It seems like it could be, but is that something people have looked at?
I think the answer is yes. So you are saying going from the tactile image to the contact. Yeah, I spent a lot of time telling my lab mates, I'm sure we can do this with computer vision. You can do something, but it's not going to be as good as the neural network. And we actually, and that's something that I still struggle with. We have improved a lot the sensor so that we can use computer vision techniques that basically do race tracing. And if you have 3 colors, there are actually very nice theoretical ways to reconstruct that depth. And for some of the, okay, let me put it this way. If you use a very bulky sensor, where aberrations that you can make them smaller and things look much nicer, you can use analytical models. But when you want to do manipulation, your sensor needs to be really thin because it needs to go into clutter, it needs to go into a lot. Then a lot of aberrations happen. And there is not a good way to solve this problem analytically anymore. And we have done a lot of design. And like there has been a person working on this for 6 months, even using like commercial software that costs thousands of dollars. And still a neural network does better with just like a few hundreds of the data. So we've tried and we got surprised by, the neural network to some degree generalizes well and does fine. And analytical models, they can do something, but suddenly a lot of noise comes and there is not a good way. And I was surprised. I was honestly surprised. I thought we could do it with filtering and it became much harder than expected.
That's cool to know. I guess the noise robustness would be much higher than neural network, as you say.
Yeah, another thing that is, go ahead.
Oh, no, go ahead.
Oh, I just wanted to add that also sometimes something that we have seen is that our neural networks to some degree can be used even for other sensors. Like you say, you change the sensor and that is still fine. Some of those analytical models would struggle a bit more to be useful for a different sensor because again, then they rely a lot on the type of illumination and they even still would require some calibration step. So the neural network has also this power that if you have shown it enough cases where it only has to detect contact, even if you shift a bit the distribution using another sensor, it still can do something. Maybe not as good, but reasonable.
Okay, that's good to know. And the other question is, so that's one of the neural networks. And then there's another neural network, it seems, that's doing some kind of contrastive learning to speed up. Is that to speed up the registration step or make it better? Or I didn't quite understand that part.
So registration of point clouds, it's something that heavily relies on a good initialization. So the neural network, what it's doing is actually doing the hard job, which is the global registration problem. If 2 things are very close, registering them is not that difficult. But things are completely far apart, that is the hard problem. And that is what the neural network is capable of doing. So the neural network is the one that is doing most of the job, and then registration is just a small part that we add just to have a bit more of precision.
I see. Because to my mind, the other option would be you keep a cache of all of the different poses, and then you just compare against all of them and pick the best one, so to speak.
This is what we are doing. We're computing.
So is the network to speed up that process, or?
The network is doing several things. The first one is that is the one that is in charge of saying when 2 things are similar, because we are not looking at pixel similarity. We are looking at pose distance similarity, which means are the poses that generated these contacts similar, yes or no? And that is something that analytically it's just not well posed. But instead with a neural network, by just showing it many examples, it can learn this metric. Then there is another property that we want to be able to compute probabilities and how to do it in a way that is not by having a proper loss. It's something that is not so clear. And with contrastive learning, producing probabilities is something that is just very natural. And finally, there is the speed thing, which is that if we just compute embeddings, then we are going from images that are to some degree big to just vectors that are kind of much smaller, just a few hundreds of numbers. And that is what helps in terms of speed, because now each of those contact shapes becomes just a small vector. And now all you have to do is compare vectors, which we know is really fast.
So would you say that you need, like, it would work much worse if you used pixel loss to do the comparisons?
Not much worse. but
Mhm.
it would do worse, because you can imagine that sometimes, imagine you have a contact that is just kind of a sphere or a circle, and one that is just a circle is a slightly bit bigger, and they are filling. Those are not that different in terms of pixel distance, but you know there is no way that they might come from the same contact. Or there are times where basically pixel distance, if you take an object that is a bit with bad intentions, it's going to do really, really bad, because things can overlap very well in terms of pixels, but then you know for sure that they have never been the same. Like imagine a donut and a circle. The only difference is the hole, but you know that those things cannot come from the same contact, because one has a hole and the one is just filling. So that's why pixel to some degree can do well when the object is relatively simple, but in the long term, it's just not gonna do well because it's not the right thing to look for.
Okay, but in your simulator, you're simulating the contact though, no? And isn't that kind of taking like naively to me, that's sort of taking a 2D segmentation of your 3D object, so to speak, or at least like raycasting it. So isn't that similar to kind of the pixel space naively?
I mean, what we are doing is we are taking the object model and we are processing in a way that it's easier for us to then use neural networks and contrastive learning, which is we are going from the object model and the pose into an image. And that definitely helps us a lot, because now we have this idea of contact, of an image that represents contact, which then can be compared with the tactile images that come from the sensor. So we do exploit the fact that we can generate images, we can render those from the object model, but then how we train them is still based on the pose distance, not on the images distance.
Okay, I see. Thanks.
Yeah, good questions.
So if there are no more questions, I have some questions, but I think it would be better to do that in one-on-one meetings. I would like to bring the meeting to a close. First of all, thank you, Maria, for playing such good sport, answering all of our questions. I think the discussion was even more interesting than the talk. It was very useful. A lot of us are working on learning from manipulation, and I think this would lead to not only just good insights, but hopefully inspire some students to either work on similar problems, perhaps ask you for advice, or hopefully even spark collaborations.
Sure. Thanks a lot for having me.
Yes, thank you. Thank you for doing such a great job on the talk. Thanks again. So I think see you next time, everyone. Arthur?
Yeah.
So do we have signups?
I didn't open the sign up sheet
Okay.
this week. I'm sorry.
No, it's fine. So I'm going to meet Maria at 9 o'clock, or well, at noon, and I'm in sort of another meeting until then. And then if students from here are interested in chatting with Maria, feel free to sign up. Otherwise, maybe it can be a break. It's up to you guys. And I'm looking forward to chatting about both future directions, but perhaps also some collaborations with Maria and Alberta. That would be cool. Thank you.
That would be cool, yeah.
See you.
I'll send you the link, Maria, over email.
Perfect. Thanks a lot.
All right.